Hello, this is Elias, and on this video, we'll be going over some of the functionality and syntax of TensorFlow version 2.0 and above. Okay, first thing that we want to do is import the packages that we will need in order to execute this notebook. If you happen to get this warning, it's just letting you know that there are some components of matplotlib that are being deprecated. You can just ignore them, or if you prefer, you can rerun the cell so that they don't show. Next step that we want to take is creating a virtual environment for us to install TensorFlow into. Essentially what we're doing is we're creating a directory or a folder, if you prefer, named VM, that it is stored inside of the current working directory as indicated by // and it contains additional files and directories that allow the virtual environment to be created and executed and maintained, et cetera, et cetera. Okay. Next step, we want to activate our virtual environment, and we do that using this command, and we're passing the command through a magic key or a hotkey. If you were to do this command on the terminal, the results would be identical, except your command line prompt would now have the name of the virtual environment you created within parentheses right before the terminal prompt itself. That's just there to let you know that you are inside of the virtual environment. Next step we take is install an upgrade pip. We need at least version 19.0 to install TensorFlow 2. And then finally, we install and upgrade TensorFlow to the newest version. In this case, it is 2.3. So next thing is we import TensorFlow as TF, and we're essentially ready to go. Just as an aside, if you happen to get a warning on this cell, take a look at this link. It will likely have the solution that you are looking for. Now some sanity checks before we start actually doing stuff. Yes, we are in TensorFlow 2.0 or above, exactly in 2.3. And yes, we have eager execution enabled. Eager execution is enabled by default in TensorFlow version 2. And essentially what it does, it allows us to treat tensors similar to NumPy objects, meaning that we no longer have to instantiate a session and do the usual steps of version 1. Now we can just work directly with tensors. And we'll see exactly what that means here in a couple minutes. But before we get into tensors themselves, we're going to take a quick segue into TensorBoard. TensorBoard is a built-in tool in TensorFlow that allows us to visualize our models, particularly how they are training. And we can plot metrics that we care about, for example, loss or accuracy. It is extremely powerful, but it does require some setup. So if you are more comfortable with matplotlib, feel free to go that route. But if you want to be able to interact with the metrics that you are tracking, this is a really cool tool to do that thing. Okay. So since it is pre-installed into TensorFlow version 2, we just load the extension so that we can run it in Jupyter Notebooks. We load additional packages that we're going to use to visualize the outputs. And then here we're creating some objects to keep track of the timestamps. Using string formatting, we're passing the information into this object, and then we'll eventually act on the object. The data itself is going to be a timestamp containing years, months, days, hours, minutes, and seconds, and it'll be associated with some callback. We'll talk about that here in a second. Okay. Next thing that we're going to do is remove the logs inside of the folder logs. In particular, what we're doing is removing all the files within the folder, but not the folder itself, or the symbolic link, meaning the absolute or the relative path that we have in memory. Okay. So now we're going to jump into training a model using Keras. We're not going to go into great depth into Keras in this particular walkthrough. Mostly we care about introducing TensorBoard, and if, as such, we're going to focus on quickly going through Keras for that purpose. In subsequent videos and discussions, we will actually go into Keras at greater length. So let's do some Keras models. So we import the data set, and then we split the data set into training and testing, and then we normalize the data. We'll talk about that in subsequent videos. Okay, so now we are inside of this function where we create the Keras model, and we are using the sequential class. Essentially what that's telling Keras is just look at the following layers. It's just a stack of layers and do them in order. The first layer is a flattened layer, meaning that it'll take the input shape and convert it to non-by batch size object. So for example, if we feed a 28 by 28 array, it'll convert it into a non-by 28 times 28 array. Next, we have a dense layer. A dense layer is just a fully connected layer, meaning that every neuron in that layer is completely connected to every other neuron in the subsequent layer. In this case, we are saying that we want 512 neurons, and then we want the activation function for the neurons to be ReLU. Next, we have the dropout function, which converts entries in our data to zeros based on some frequency that we determine. In this case, it is 0.2. This is done to prevent overfitting. Just a key thing to keep in mind, the more neurons your hidden layers have, the more closely you approximate the actual information you're trying to fit. So for example, the first neuron may look at a dot, the second neuron may look at a line, third neuron look at a curve. By the 512, you may actually be able to approximate, for example, the shape of the letter G. But the problem being that you will likely train the model so well on the training data that it will not generalize well. And that's why we use dropout. And then finally, we have a dense layer with 10 neurons and an activation softmax. This is just us exiting the last layer of the neural network. If you want to know more about the specifics of these layers, you can learn about that here. So let's go ahead and prepare our object, and we're ready to go. Next, we're going to create a model. Let's look at a couple of things here. So we have compile here, and essentially what this class is doing is taking a graph of the layers that we've created, and then using that particular data structure to run the computations on. What that means essentially is that you can use that object to debug. So writing Keras code is an awesome way of doing deep learning because it handles debugging for you. If you're using something like gradient tape, you have to debug without the actual object, that is the graph, which can become extremely complex, particularly if you're not very familiar with the process. Okay. The next thing that we're doing here is we're creating some logs, and we're associating the logs with the callbacks, which are being passed to the model itself. And then finally, we fit the model, and we're doing 5 epochs. The epochs are an entire pass through the training data set. And let's go ahead and run this cell. It shouldn't take more than a couple of seconds. And we see how the accuracy is changing, how the loss is changing as we're going through every epoch. Just a thing to keep in mind about Keras is that it is an extremely simple way to build neural networks. So let's go ahead and take this guy out just as an exercise. So here we have 2 layers, a flattened and a dense layer. This is essentially a linear classifier, a multi-class logistic regression classifier to be exact. If we undo that change and we add an additional layer, here now we have a neural network. And if we return the layer that we removed, now we have a deep neural network. So as you can see, just by the use of a comma and the keras.layer class, you can essentially continue to add however many layers you want into your deep neural network. It's a super easy way to build models. Okay, so let's see if our model is done training, and it is. If you want to learn more about the particular classes that we're using here, you can use these links. And let's go ahead and display our logs. And here we see the epoch accuracy and the epoch loss. You can actually select the level of smoothing. You can select the type of tooltip that you want to have. So it'll change some of the information associated with the plot as well as the interaction of your cursor with the plot itself. In this case, we only elected to look at accuracy, but essentially you can add whatever metric you care about and it'll allow you to fully interact with it. It's a pretty powerful tool. Okay, so let's leave TensorBoard behind for the time being and switch to TensorFlow Tensors themselves. So TensorFlow Tensors are highly efficient multidimensional arrays that allow you to work with data from anywhere from a scalar to an n-dimensional data object. They are essentially multilinear maps from the vector space to the real numbers, meaning that they can fully represent scalars, vectors, matrices, etc. Tensors also have object life cycles that are similar to Python objects. So for example, if you declare a tensor, but you don't reference it in your code, it is ignored and deallocated, which is pretty awesome. So let's look at TensorFlow Constants. They are immutable tensors that are initially declared. And you declare them essentially how you would expect. You create in a tensor and you pass a value. In this case, we're passing the number 4 by itself, meaning it's an integer. So we're creating a rank 0 tensor. that is a constant 4. If we use the eager execution, we can see that it is the value 4 is what we have in there. You can also name your tensors. This comes particularly handy when you are building your own either optimizations or your own gradient descents, whether it's piecewise forward or piecewise backwards. You can pretty much fully and granularly architect your neural network however you want it. The naming of tuples comes in handy during that aspect, or the naming of variables in general, which is also allowed. Okay, you can create vectors as you would expect, and since constant tensors are immutable, if we try to change it, we see that we can't. Okay, next let's look at Tensorflow variables. They are tensors that are used to store data that changes. So for example, the weights and the biases during training, they are automatically assigned the optimal data type for processing speed if none is declared. And they can be associated with a different architecture. For example, you could have a variable or a collection of variables be associated with GPUs, and a different collection of variables be associated with CPUs, and then have them interact together, which is a pretty neat architecture solution that allows you to solve some really interesting problems. But let's move forward. Here we create a variable. We're passing 3.0, which is float, and it automatically designates it as a float 32. Variables are mutable, so we can use the built-in methods to assign the original value of 3.0 to 4. And if you notice here, we're passing an integer, but it does data type coercion, so it converts the 4 to a 4.0, meaning float, even though we passed an integer, so something to keep in mind. So let's look at multidimensional tensors. Here we're passing integer values, but we are declaring the data type to be float 16. So if we run this, we see that indeed the values are float 16. You can use distributions to build tensors, meaning that if you wanted to do an array of zeros or ones or something that models a normal distribution, you can use functions that allow you to build arrays like that, much like you can in NumPy. So the thing that you may have noticed by now is that if you can do it in NumPy, you can pretty much do the exact same thing with tensors, but the syntax will be a little bit different, but essentially the result will be kind of the same in the sense that tensors are essentially like NumPy objects, but that are that can run on GPUs, and we'll talk more about that here in a little bit. So you can build tensors from Python and NumPy objects, and then using built-in methods, you can extract the attributes of these tensors, just as you would expect with NumPy objects. You can do some advanced operations on them as well. Here are a couple of examples, and then you can do variable assignments as you would expect. Then here we see something to note about tensors. Here we have two different dimensional tensors, and if you notice, they are not compatible, meaning we can't perform an operation that combines the two as an example. You can do Tensor Broadcasting, just like you can NumPy array broadcasting, and that is covered in the optional section. But generally, what you want to do if you're unfamiliar or uncomfortable with broadcasting is you want to massage the smaller of the two arrays so the dimensions line up, and then the way you can actually operate them both. Okay. And then here we have Tensorflow Assignment. What we're showing here is that essentially you can use the memory reference to affect a different tensor. So just something to keep in mind is that pass by reference is present in TensorFlow. Okay, so now we can look at the exact same tensors and how you can change them using built-in methods. Okay, so here we introduce a 3-axis tensor or a rank 3 tensor, and it shows you that you can just build it off of lists or arrays. You could pass a Python dictionary as an example, but that's a little bit tricky because you would have to assign the keys to the names, but we'll discuss that in a future video. But essentially the key takeaway is pass arrays and you can create a rank 3 tensor. As an exercise to make sure that you understand the concept, you can build a 4-rank tensor with these particular scales. Okay, so we won't discuss life cycles, naming or watching. It just means that arrays, not arrays, I apologize, tensors behave a lot like NumPy arrays with a lot of Pythonic-like elements. You can go through these cells if you want to explore that topic at greater length. You can place variables and tensors. So before I mentioned how you could have a collection of variables in GPUs and some in CPUs, here's an example of how to do it, and you can get pretty advanced. Just click on this link for more. Okay, so now let's look at TensorFlow operations. As you would expect, pretty much everything that you are comfortable and familiar with in doing in NumPy, you can do in TensorFlow. And here's just a visual association to allow you to carry forth that reference. So you can use built-in methods to add them, or you can use operator overloading, the same with multiplication, the same with dot products, and et cetera, et cetera. So now let's get into tensor operations. So we're only going to cover a couple for the sake of time. If you want the complete list, just click here. But as you can see, you can compute the maximum of an index. You can find the location of that index. You can compute the softmax of an array, which is pretty neat. So now we get to gradients from scratch. So normally your gradients and the way that you architect your gradient is done automatically by Keras, which is why Keras now is pre-installed in TensorFlow. However, for research purposes or unusually demanding implementations, you may need to build these things from scratch, and this is how you do it. The reason why we're covering this is because you will need it for the homework. So we import some libraries that we'll need. We create some noisy data that resembles a model that we ultimately want to represent, which is y equals mx plus b plus some noise. We get some data using the function that we created above, and then we plot it. Next thing that we do is we declare some variables that are going to change over training. And we have the model itself. And then we declare a function that we care about to keep track of the error. And then finally, we compute the loss prior to training. All of these steps would normally be done by Keras, and you would never have to build this. This is just an exercise to show you how it functions. Okay, so now we finally use the class gradient tape to do the process that is normally automated by Keras. In this case, what we're doing is taking a number of steps and we're keeping track of the loss. And then at the very end, once we're done through the 200 steps, we see the gradient that was computed at the very end. Okay, this will come in handy during your homework. Feel free to pause and replay this section if there's value in that. Okay. With the last few minutes that we have left, we're going to show that tensors can be indexed and sliced, just like NumPy arrays. So we create a tensor. Here we are using integer indexing, and we can see that we can take values out of the index. We can do single axis slicing, just like you can in NumPy arrays. You can do multi-axis indexing, again, just like NumPy arrays, and the same being true for slicing. You can also manipulate tensors. You need to use the built-in functions, just like you would with NumPy arrays. Okay, so we'll move past that, and then we'll skip broadcasting tensors. The key takeaway is that it's essentially the same idea as NumPy array broadcasting. And what that means is essentially if you have two arrays of different dimensions, you can take the smaller one and automatically augment it so that you can work with it in conjunction with the larger array. Alternatively, you would have to do this manually. Broadcasting is pretty powerful, but we won't cover it in this tutorial. You can just take the time to go through it if you care. And then if you're working with unusual tensors, there's some links here to give you additional information. This is very real world, but not for our purposes of this tutorial. Okay, so now we get to the TensorFlow computation function, which is the new way of doing TensorFlow. Prior to TensorFlow version 2, you would have to instantiate a session and then do a bunch of additional stuff just to be able to visualize a tensor as an example. Now you can just use the addTF function, the decorator function, and it'll essentially do everything for you. And what the addTF dot function is doing is essentially telling TensorFlow, hey, I want you to take this code, trace the entire execution of it, and then I want you to optimize it in C++ and run it. So essentially, it's acting, as I said before, just like NumPy, where it's taking your Python code, optimizing in C++, and executing it without the need to having to ping pong between Python and C++, except it can run your code in GPUs and TPUs. Key takeaway from that little speech is that if you are in TensorFlow version 1, you want to get away from it because it's much harder. And the way that you know that you're in TensorFlow version 1, particularly as you're looking for information out there on the web, if it has the word session, just move away, or the word placeholder, just move away. If you see the @tf.function, you know you're in the correct place, or if you just see placeholder and sessions missing, you know you're in the right place. Okay, so let's look at the @tf function. Here we create a function, we pass some constants to it, and it does what you would expect it to do. So a neat thing about the decorator function is that it allows you to export a safe model. So what we do is we create the variables and we pass it into the function. And when the function is ran, it converts the entire thing into a graph. And the graph itself is an object, meaning that after we've, for example, trained a model and saved it, we can export that object into, for example, Android and be able to run the exact same model in Android, which is super powerful. But we will discuss that more in subsequent videos. Okay. The decorator function can handle your normal control structures, as you would expect. It can function with constants and variables mixed together, but it does have some side effects. So let's look at some of those here. So we create the function, we're adding to C, the object that we create right here. And then we look at C, it's numpy4, which is what we pass, it's an integer value. And then here we're running the exact same function call, but we're passing the value 3. And if we notice, it's actually adding the value 3 to the previous value. So we're actually acting on the variable itself. That's not necessarily a bad thing, that's just something that you need to keep in mind, because you may be accidentally either changing the value of your mutable object or potentially the binding of a global variable, which would be potentially a very bad issue. Okay, so let's look at handling side effects. So here what we're trying to do is we're going to pass constant tensor and we want to append 1 to the values. If we do that, we see that it returns none. So let's explore what's going on here. We see that it is a tensor of 0 shape that's adding 0 because essentially nothing is happening here because L is empty. So now let's go ahead and pass an argument and then rerun L. And what you'll notice is that even though we're passing a variable here, so let me go ahead and do a print statement here just so that you can see what's going on. It's still doing none. So what's happening here, it's not performing the thing that we would expect, which is append +1 to it, each element in the tensor. Instead, it is creating an additional tensor that matches the original. So it is misinterpreting the effect that we want. So now let's look at how we handle that situation. In this case, we want to do the exact same thing, which is take the elements in the tensor and add 1 to them. And we do that using this function. In particular, we use the write method here. So we run the cell block and we run this, and now we see that we're actually acting on the tensor itself. Okay, the decorator functions are polymorphic, meaning that you can pass various data types and the function will act on them. In this case, we're passing an integer 32 and then float, and the computation is performed on both. Hidden side effects may be a good thing or a bad thing depending on what you want. So let's explore where we would care about such things. So here we're using getConcrete function method to get the exact memory location of the graph. And the reason why we care about it is that maybe we want to use different graphs. So for example, when we were saying that the decorator function is polymorphic, each time that it runs with a different data type, it recreates the graph, but it does it anew, meaning that if you do integer in the first one and then a float in the second one, those are different graphs. Not necessarily an issue if that's what you want, but whenever you have a decorator function creating a new graph, you are essentially adding more memory expenditures to your process. So sometimes being able to maintain the exact same graph in memory and then reusing it on the same data type is advisable. And we're going to look at that example here. So if we look at these two as an example, they have different memory locations. Now what we're doing here is trying to keep the same memory, and we see that they are the same. So super neat. Okay, now let's look at input signatures, which essentially is another way of looking at this problem. We can declare the type of input signature that we want, and then we can reference the input signature, which means that we can maintain the same graph and then reuse it for our purposes, which is something that we discussed. And then you can see the entire process and output here. Okay. Some final comments and some other observations that you may want to be interested in. There's also additional information on installing TensorFlow here if you need help. Also how to create a virtual environment. And then finally, some additional content and resources in case you feel like you are getting stuck or you need some help moving forward. That's about it for our introduction for TensorFlow version 2. In additional and subsequent notebooks, we'll cover Keras at greater length, as well as various types of neural networks and how they are applied and optimized. Wish you the best of luck. Goodbye.